Good morning, everyone. My name is Kelly Kane, and I'm the Marketing Manager for EandM. Thank you for attending our PLC Programming Best Practices webinar today. After the webinar this morning, we will be doing a short Q&A. Please type any questions or comments into the Q&A box, the chat box, or email us at eandmwebinar@eandm.com. Now I'd like to introduce your presenter for today's webinar, Bill Hintz. Bill has been working with Siemens Automation Products for 25 years as both an OEM machine designer while with James River Dixie Products, and also with Agilent Technologies as an engineering manager. Bill is currently an EandM Siemens product specialist working with customers to design new applications for Siemens products. Good morning, Bill.
Good morning, Kelly, and thank you. Welcome everyone to the Best Practices webinar. Today what we're going to be talking about a little bit is the TIA portal software and configuring some portable code and so forth that kind of best tips and tricks that we can to use to architect new projects and save code and things that we've developed for later use. I mentioned we're going to use TIA portal today, and TIA portal actually, those of you familiar with the Siemens S7 line, there was the S7-200 originally and the 300 and 400. 300 and 400 is still with us, going to be here for quite some time. They're talking about into the 2020s. But at the same time, we're going to have this parallel path with the S7-1200, kind of in the middle range, and the new S7-1500, which actually not quite so new now. It's been out for over a year. And that's what we're going to use today, is the 1500. It actually is similar to the 300 system. Those of you familiar with that, it's a modular design. So we have CPUs and I/O modules, and they fit on a DIN rail and create their own backplane as we go. So there's little U-shaped connectors that will actually fit behind the modules and interconnect as we go out on the DIN rail and create a bus as we go. This is a little bit different than the rack-based PLCs that you've seen, where you buy an 8-slot rack or a 16-slot rack and then fill it up with I/O cards. This way we just kind of make it as we go, and actually the 1500 allows us to go all the way up to 32 modules on the local rack. Okay, so I'm going to go jump over into my TIA portal screen here. So if I click my other monitor, that should pull up the TIA portal software. And this is actually what's called the portal view. So when you originally open up TIA portal, this is the screen you see. And it allows us to open existing projects, create new ones. You can migrate an existing older platform project into TIA portal by using that. There's actually some kind of neat little video tours. You can actually go in and see how to do individual items in TIA. So this is kind of a neat little function if you want to look specifically at 1500 motion, for example. Installed software tells me what we've got loaded into the box right now. Now I'm using the professional version, and there's really two flavors of the TIA. There's the basic and the pro. The basic, the only difference with that is that the basic just does the 1200, and the professional actually allows me to program a whole host of different devices, and I'll show you about that in a moment. So let's go ahead and jump into what's called the project view. Actually, I'll create a new project first. Let's just call it webinar. That'll do that, and it gives me a different screen here where I can configure a device, write PLC programs. I can do an HMI, do drives, and all these different components of an automation project that the TIA portal lets us program. I'm going to go into the project view, and this is kind of a same look and feel no matter what we're doing in TIA. In the project view, we're going to have what's called the project tree. We're going to have a work area in the middle, and then we have a context-sensitive task list over on the right. So this may be instructions if we're doing ladder logic. It may be hardware if we're configuring a device and that kind of thing. Let's see how that works. Let me go ahead and add a new device. Here we can do HMIs, PCs, drives, controllers is what we're going to do first. And as I mentioned, I am in the pro, so I see 1200, 1500. We can also do 300s and 400s in the TIA Professional. So let's pick a 1500. I'm just going to go right here in the middle and say a 1515, which is kind of in the mid-range of the different processors. There are some new, anytime you see an F series at the end, that's a fail-safe or safety processor. Those are kind of the new releases. I'm going to go ahead and just pick the standard 1515, and it's going to go ahead and import that into our project. And then what we see when it's done is it's going to pull us right into the hardware configuration area. It's called Device View. See up here on the tab. And you'll also notice that our context-sensitive task area has changed. So now I have a hardware catalog. So if I wanted to add, let's say, some I/O, I'll just pick a digital input-output combination module. Double-click it. It plunks it right in there. I'm going to actually see now over in my project tree, I've got the PLC that I've added. And I have some local modules that will show the actual module that I just put in, the PLC. Pretty simple. Okay, once we've got a PLC in the project, we actually see it's got a whole bunch of different things we can do in here. The device configuration is where we are right now. We can go down here to program blocks, and Siemens actually gives us one gimme block. This has been standard for Siemens PLCs for years and years. It's called OB1, or Organization Block 1, the main PLC scan block. So PLCs, of those of you not familiar, actually, for the most part, what they will do is they're going to read their inputs coming off of input modules. They're going to run any code that they find inside of OB1. Then they're going to update their output modules, and then they're going to do it all over again. Read the inputs, run the code, write the outputs, do it all over again. There's some other stuff that goes on in the background, like diagnostics and watchdog timers to make sure that everything's okay. But for the most part, main OB1, that's what it does. And so now when we're in OB1, we actually have a ladder logic programming environment. You'll see over here our instructions have shown up in the taskbar, and now this gives us all the different instructions of the PLC that we've selected. I've also got a favorite areas, so if there's something that I like to use a lot, then I could actually, let's say, I don't know, a comparator, compare if not equal. If I drag that up and put that up here, it's actually going to show up my favorites area, and I don't have to go looking for it every time. So in any case, let's write a little simple code just to get an idea about the environment here. We're going to do a little ceiling circuit, and ceiling circuits are typically how ladder logic was designed to simulate what a relay logic schematic looked like. So we actually have a power bar, and we're going to pass power through if different contacts and so forth have closed. So if I just go ahead and grab a normally open contact and bring it down into the first network there, that would be, for example, a start button. Now a coil is actually an output. So this contact is going to reflect the status of an input point. The coil is going to be an output point. So if I push this button, let's say that's wired up to that input point, we're going to have power flow and turn on. If this was a motor, a pump or something, it would turn on. When I let go of the button, it would turn off. That's all fine and good, but not typically the way we run motors. Motors typically you want to push start, then you let go, and it keeps running. And to do that, we create what's called a ceiling circuit. You'll notice as I grab things and bring them down, it gives me little green squares where it's okay to place them. If I want to put a ceiling parallel circuit right there, I can just grab it, stick it there, and now I've got a contact in parallel with my start button. So for example, if this were our pump 1 start button, this might be pump 1, and then we would have the same name for this ceiling circuit, pump 1. What that means is once the power flows into pump 1 and it turns it on, we're going to actually also look at the status of the pump, and if it's on, it's going to remain on. We'll actually be able to seal the circuit in, and it latches it. That's all fine and good until you want to turn it off, and right now we don't have any way of doing that. So we would actually put in another contact in here, and typically a stop button is normally closed. So we'll just say, call this one pump one stop. And that's great. Simple circuit. This has been used for years and years. What happens if we have a bunch of pumps? If we wanted to have 10 pumps, then we would have row after row of the same logic going over and over again. And that would work. It just it gets a little tedious. This is what we start calling spaghetti code, because it gets so long. And this function is actually the same thing going over and over again. And those of you familiar with software programs, we call those perfect candidates for subroutines. So a subroutine in Siemens land is actually when they create what's called structured programming, we use things called functions and function blocks. So if I were to add a new block, it shows me all the options here. Now the first one we used was this main OB1, and these OBs are called by the system. So the main block is called by the system every scan. There's other OBs for startup. If you want to pre-program or latch something or do different set points when the thing first starts up, you can write code in startup OB, and it will only run once when it first starts. And there's a whole host of different diagnostic type interrupt blocks, all kinds of things like that. In our case, we're going to write a user-defined function, so it has to be called. So if I grab on function, and we call this pump, for example, we're going to get a whole new template of data area where we can actually write another subroutine. And in our case, I believe I copied and pasted. So let me see if I'm lucky and just go paste here. Yeah, I still got my code there. So now what we can do is we actually have this code that we can look up above in a function. What it gives us above is called a declaration table. And declaration tables allow us to pass parameters into a subroutine. So when we call it, we could actually give the addresses of our push button for the start, our button for the stop, and our pump output. So let's go ahead and define those. If I go say input, I'll call this one, if I could type. You'll see if I name them properly, then they just come up here with a little hashtag in front of them, and that just tells me that it came from the declaration table. We can do absolute addressing of symbols and so forth that wouldn't be coming from the table, and this just differentiates it. So let me see if I can do this. It wants me to write it out. You'll see it define these as Booleans, and Booleans are just single bits in our logic. Now, if we look at our pump is not an input. We put these other two in an input area. There's also an output. There's a third one here called in-out. And if you look at the way this pump one is defined, we're actually looking at it as an output, but also as an input. And in-out just allows the block, when it's called, to both read it and write to it. So we're going to put pump one into an in-out area. And now we have code that is actually going to be able to allow us to go back. If I go ahead and compile this, make sure everything's happy, we'll go back to OB1 and go select all the networks and delete them all out. Now, I can call this subroutine rather than writing all the code in OB1. And now I have a pump one. I can do another one. And what we'll do is we'll just pass different addresses for the different addresses of the pump itself. And I probably shouldn't call that pump one, since this is going to be a global block that could be any pump number, but that's okay. So in other words, you get the concept there that we're actually going to be using a subroutine that we can pass parameters to and call it over and over again without having to see all the logic in our OB1. And OB1 can end up looking like much more like a table of contents, where we can actually, if I right-click on FC1, I can say open it, and it shows me the logic. Also, by the way, if we had multiple calls of this block, that all had different pass parameters in there. If I open it and monitor it from the call point, it will actually just show me the pass parameter values that are for that individual call, which is a pretty important point if you're troubleshooting code. So that's the gist of how we would actually create a subroutine, a function. Let's create another block. Let's do something with a little bit more complex, maybe some mathematics. I'm going to create a block. Let's say this pump is filling up a cylindrical tank, and we want to calculate the volume that's in the tank. So I'll call it volume. Now we're going to do this in ladder logic, and ladder is not the ideal language for mathematical functions, but it'll work, and it gives me a chance to show how we can use some internal functions in a subroutine that actually allows code to be portable. So if I remember correctly, the formula for a cylinder is pi r squared times the height. So I'm just going to say, let's do the r squared first, times pi times, and this is just a title so that we remember what we're doing here. Now if I go over and look in my instruction tree, I can actually pull out some math functions. The first thing we're going to do is that squared function, and I'll pull that in. And then we're going to multiply that by pi, so I'll do a multiplication block. And we're going to multiply that by height, so another multiplication block. I'll zoom this out a little bit so we can still see everything. So the first thing that's going to come in there is going to be an input, which is going to be our R radius, the radius of the tank, and then we're going to bring that in as a real number. If I type the first letter, it'll give me all the R's and reals there. And then we're going to do the radius times pi times the height. Also a real. And our output is going to be volume. Okay, so to do that, I'm going to go square my radius. And then the output of the square block, I'm going to put in, I need a kind of a temporary tag here, so let's just call that scratch. And define a tag, and it's going to pick the first internal memory area available. M is an internal memory area. It's a double word, so MD, and it's a real. So if I pass that scratch, so the radius squared is in scratch, we're going to pass that to scratch also, and multiply that by pi, which, if memory serves, is something like 3.1416, close enough. And then once again, we want to pass the result of that into our next block so we can actually multiply it by the height. So let's use our scratch again. We don't care about what was in it before, so anytime you write to it and read it immediately, that's a perfect example of a scratch. So I'll go ahead and hit scratch there, pass that in to our multiply block, multiply that by the height, and our result is the volume. So if everything works correctly, we're going to get square of the radius times pi times the height, and that's going to give us the volume of the tank. Now the height's probably going to be coming in from some kind of an ultrasonic sensor or something at the top of the tank. So as that tank rises or falls, this will calculate the volume that's inside the tank. Okay, so let's go ahead and compile that. Everything looks okay. Go back to main OB1. Now I can calculate the volume. So I would bring in the radius, whatever that is, of the cylindrical tank, and multiply that by the height, which is coming from our sensor, and the output would be the volume. And we can call that over and over again. And that's all fine and good, and in fact, the scratch flag issue in there wouldn't really hurt us if we're using this over and over again, because we use it and read it, and then we don't care what happens to it. But the idea that we're trying to stress today is something called portable code. And portable code allows us to store code in libraries and bring it into future projects, so that if there's some volume function that we need in the future for a cylindrical tank, we can actually pull it out of the library instead of doing what I just did and starting from scratch and writing a whole new block. The one major problem with that, with the way this is written, is that what happens if we pull that into a project that is using these absolute addresses already? So that M double word internally may very well be being used somewhere else in any future code that we're going to bring this block into. So we need a better way of doing that. And Siemens gives that in our function here called a temp variable. So I can have a temporary variable that's just for the call of this block, which is perfect for things like scratch flags. So let's go ahead and create one. Scratch flag, make it a real. And now, actually, we can type that, and you'll see I've got a scratch, which I defined as a absolute address, but also the one with the hashtag in front of it, which is our instance of this block call, temporary area. So now if we look at our code, it looks like I put my new favorite up there in. Now if I look at my code, I see every one of my parameters in the code, with the exception of this one constant, which is okay, has a hashtag in front of it. So that means that we're not going to have any problems in storing this in a library and using it in the future. Let's see how we might do that. Let me go ahead and click on libraries. And over here on the far right, there's several different little areas that we can access in this context-sensitive area. And the project library is a library just for this project. Global libraries we can actually create and store, and we could put it on a server or something, and then if we have multiple people working on different projects, then they can all access a global library. Let me go ahead and create one. I'm going to have this on my local PC, but we could be putting it up on a network storage device. I'll go ahead and create a library. Now I've got that library, and I can put into the library something called master copies. And to do that, all I need to do is, let's say we're going to store our volume block. Drag it over, drop it on master copies, and now I've got that volume block for future use. Once we've tested it out, know it works pretty well, put it in the library, then we can reuse code that we've written before and not have to, well, you work it once and you get paid for it a bunch of times. That's the way I look at it. Anyway, so that's all fine and good, and it actually kind of gives us the idea of how scratch flags work in portable code. But let's look at a different application. Let's go back to our pump function and make this a little more interesting. So I'm going to go ahead and insert a new network. And let's say we want to actually look at something more long-term on our pump function. Let's say we want to have a service light after a certain number of hours have been run on this pump. How would we do that? Well, we've seen that the pump, when it's on, this contact's on, so I can just go ahead and copy that guy. And now anytime that pump's on, we're going to pass power in. And let's go over to a timer function. And there's various types of timers. There's pulse timers, on delays, off delays, and all this. But there's also something called a time accumulator, which works really well for like hour meters, and that's kind of what we're doing here. So I'm going to go ahead and put that guy in here. And what it does is functions that require memory long-term, things like timers and counters and other stuff like that, actually need a instance data area for that individual timer in this case. So we're going to go ahead and allow it to create a data block for that timer. And let's say after 100 hours, 100H, we're going to turn on a light or something to notify somebody that it's time to go out and take a look at that pump. So we'll call that one service. That's an output. So there we go. So anytime the pump's on, we're accumulating time. When it hits 100 hours, we turn on the light. Pretty simple stuff. It's going to probably make my OB1 squawk here because now we've changed the block. So it knows we've changed it and wants to make sure that we know that we're calling a block that's different than the one we've recently edited. So if I just go update, it'll say this is what we had before, this is what we have now, which actually now has this service output on it. So we're going to go ahead and hit OK, and everybody's happy. Fine and good. Now, let's say we wanted to store the pump function in a library. We're going to have a problem. And the problem there is that we've created really an absolute address here for this timer. And it's created a data block for that timer. And if I call this, even if I don't put it in a library, if I call this block multiple times, it's going to call that same timer every time the block is called. So we would be accumulating for several pumps if we called this for a dozen pumps, for example. So how do we get around that? To do that, we're actually going to generate another one of the blocks that we saw when we hit the Add New Block button, and that's called a function block. And the difference between a function and a function block is a function block has its own instance data block that comes along with it, much similar to what we saw with the timer. So I'm going to call this one pump and timer, just to be clever. Once again, we've got the same ladder environment. I'll go ahead and go in here and copy all the stuff that we did here and put it into our pump and timer block. Got some inputs and outputs, so it's, we just call that pump start. And fix my earlier error. I didn't want to name it an actual pump number. So now we just go pump start, pump stop, and pump. That's better. Pump. Oops, I didn't do a service one yet. There we go. So we've still got the issue with this DB1 in the timer block, and how do we get around that? Once we're in a function block, we actually have a new area. Did I create a function block or a function call? You know what, I did a function call, didn't I? Oops. Let me do this proper way, function block, thank you. Really me? See the blue there for a function block as opposed to the green for a pump and timer. One more time, bear with me. My code's still there. Come on down. So How fast can I type? Pump 1 start, pump start, sorry, pump stop. Pump. Okay, now we look up here and we see actually we've got something that we didn't have in the other ones. We have our temp area, but we also have what's called a static area. And that's the difference between a function and a function block. So the static area allows us to have data stored between calls. And actually when we do multiple calls to this block, it has its own instance data area that it can save things like timers. So if I right-click on the timer, it actually allows me to change the instance of that timer block. Whereas before I just had the single instance, now we can call it a multi-instance. And I'm going to call that hour meter. So now we have a timer with an hour meter data area, and you'll see that shows up there in the static area. Should be able to compile this guy. Everybody's happy. And now, clear some things out here. If I call a function block, pump with timer, and stick it in there, once again it comes up and says, what do we want to have for our single instance data block for a function block? And we can call this one pump 1. We can do it again. This time we call it pump 2. Now we have calls of a block that are totally portable. This is if I open this block again and go through it, we have not used any absolute addresses. The only absolute address that happens is during the call of that block, which is this instance data block. And that's fine because that's fine for every different pump that we call. And this allows us to actually write code, store it in a library. And now we can pull it into a new project or an existing project that has a lot of code in it already without fear of actually stepping on anything that is in the existing code. When we pull this pump and timer block into our old project, it's going to actually ask us for a data block instance call, and it automatically only picks data blocks that have not been used yet. So we've created a whole new template area that we don't have to worry about anybody else's data areas, what their internal memory databases look like, or anything else. It's portable code, and that's the kind of the concept we're trying to get across here. I do have a couple of questions that came in here, and one of them is, can you save block comments in the library? Okay, let's go ahead and I'm going to go ahead and delete my volume block here, just to kind of show, because I think we put comments in that one. If I pull in from the library the volume block and double click on it, you'll see that we do have comments that have come in with it. So all the different things that are programmed into that block are saved in the library. And libraries can be used for a whole lot of different things. Actually, we can store entire projects in libraries. We can store, for example, we can store this whole PLC, including the hardware configuration, all the code that we've just done and so forth. I can just drag the whole thing over and drop that into a library. That'll take a little longer to digest. But now I've got a copy of that PLC. So if this is a PLC that we're going to use for a lot of different applications, in the future I can start with a whole new project, pull this in out of my library and just drop it in, and we're reusing all the effort that we've put in so far today just to configure the hardware, the software, and anything else that we had done for that PLC configuration. Pretty powerful tool. Okay, another question I've got here, is the 1500 faster than the 300? You know, it's funny because PLC, this is a common question about PLCs and how fast they are and so forth. You know, one of the reasons that companies come out with new platforms is actually because, for example, the SM300, its backplane it has what's called a K-bus, and that's a communication pathway to go to higher-end modules. So if we put an Ethernet module out on the I/O bus next to a 300, it's going to communicate over that K-bus. And at the time, in the mid-90s, when the SM300 came out, we were still talking about 9600 baud and so forth. The backplane K-bus is 187.5 kilobits per second. So that's actually, at the time, fairly fast. Today, not so much. So what they did is when we look at the 1500, it's actually going to have a backplane that, for example, the 400 was a 10 megabit backplane. The 1500 is 40 times faster, 400 megabits per second. So far as the actual raw speed, I think I've got a slide in here for I'm going to have to change screens here for a second. Bear with me. That's not. It's not cooperating. But actually, I'm looking at this other slide here. It's actually the new 1500. The highest end processor is a 1518. So it's running 1 nanosecond for a Boolean operation, which is, what, 1 billion operations a second? Don't know how many ladder logic instructions you're going to need, but 1 billion of them is quite a few. Anyway, the speed of the processors is similar. I believe the 319, which is the fastest 300, was somewhere around 3 nanoseconds, so they're similar. But where actually the improvement is being made is on the infrastructure, the backplane speed of the new 1500. Okay, question: what other instructions require data blocks? Oh, okay, like the timer, I guess. Let me let's think about that. What else would be? Well, a counter would be anything that needs to have a memory to remind itself of where it was before. So, for example, if I wanted to put we use a counter, you know, we could count how many times the pump started. I could put a counter function in. How would I do that? Just go ahead and stick that right there. So I'll do an up counter. Probably should do it in our function block, shouldn't we? Let's do it down here. Counter. So we'll count how many times the pump started. As a multi-instance. And then we'll tie its output to the service light too. And also from the pump. And so at every 1,000 starts of the pump, let's say, we will turn on the service light. So yeah, and if you look up above here in our static data area, it's now created another area for the counter. So there are any of the functions that require some kind of a memory are going to use this instance data block concept. Okay, well, that's all the questions that I've got here and pretty much everything that we wanted to cover so far as portable code and structured programming. Appreciate your time today, and thank you very much.
Great, thank you, Bill. And if anyone would like to review any portion of this webinar, a recording will be available on our website, EandM.com, later this afternoon. Thanks, everyone, for attending, and have a great weekend.
Bye now.
Bye.